Hello everyone, welcome back to Control Systems Lectures. In today's lecture, I'll be dealing with a topic which is one of my favorite topics. It is actually a very powerful and insightful technique which is used to analyze and design control systems for proper stability and transient response. And this technique that I'm talking about is known as root locus technique. It was basically introduced in the year 1948 by a person known as W.R. Evans. And this is what he derived. In the name itself, you can see over here that there is one term that is root. So here we are talking about the roots of a system. As you already know that if you have any system, then that system's transfer function, it can be represented by a function of numerator and a function of denominator. Okay, and then the roots of the denominator ds, they are actually the poles of the system. So here the roots are the closed loop poles of a system. The roots that we are talking about are the closed loop poles of the system. And the second term you can see over here, it is locus. Locus is actually a path traced by a point. That is what we have learned. So here we trace the path of the closed loop poles of the system. So these are the poles, we trace the path of the closed loop poles of the system. But why will the pole trace a path? Means you know that for a system, if it is given, then you have for particular system you can have two poles, and suppose you have got a zero over here, so they are fixed. So why will this pole trace a path? So here comes the logic. We actually trace the location of the pole when a system's parameter is varied. So suppose for example you have got a transfer function which is represented like k upon s plus k, where this k is actually a variable. So this k I am taking it as a variable. Then as the value of k, if this varies, if we vary the value of k, suppose first of all k is equal to 0, then you can see here the pole is actually s is equal to minus k. So the pole's location will be at s is equal to 0. Now if I vary this k, if I vary this k and make its value as equal to 1, then the pole's location will be s is equal to minus k, or pole will shift to s equal to minus 1. Similarly, I again vary the value of k to 2, the pole's location will again change to minus 2. So here you can see, if I again want to plot this transfer function's poles, the system's pole on the S plane, then as I am varying this value of k, the pole is actually moving. This pole is actually moving from k equal to, when value of k is equal to 0, then the pole was at s is equal to 0, and as I varied it to 1, this pole shifted, it came here at minus 1. Then as I varied it to k equal to 2, then the pole again shifted to, this came over here as minus 2. So the k, as the value of k is varying, the position of the pole, location of the pole is also varying. Okay, so this is how we can trace the path of the pole. So as the pole varies, we trace that path. But why is the need to trace the path of the pole? This is the second obvious question that can come. We need to trace the path of the pole because the closed loop poles, they are very crucial. They are very crucial to us. For stability, we have already discussed that for stability, the closed loop poles of the system, they should compulsorily lie on the left hand side of the S plane. So if you want the system to be stable, then all the closed loop poles of the system, they should lie on the left hand side of the S plane. To understand this better, let us take another example. Okay. Suppose I am now taking a second order function. So I am taking a transfer function. Okay, let's take the open loop transfer function for a system. So let's suppose the open loop transfer function, that is GSHS, that is given as equal to k upon s into s plus 1. Suppose this is the open loop transfer function of a closed loop system. This is OLTF. Okay. So the system's transfer function for any generic control system, if GS is the forward path and HS is the feedback path, and the transfer function, it comes out to be equal to GS upon 1 plus GSHS. Okay. So here we define this term, that is 1 plus GSHS. This is actually known as the characteristic equation. This is known as the characteristic equation for the system. So the denominator's function that we get in a transfer function, that is defined as the characteristic equation, and in the characteristic equation you can see this term GSHS. Hence, if you are given this term GSHS, then you can easily derive the characteristic equation by adding 1 to it. So if ever I am given a problem where this GSHS is given, then I can easily say that this GSHS is actually, then I can easily find the characteristic equation by just making 1 plus GSHS. This will be the characteristic equation. So here, if I do the same thing, that is I am doing the GSHS, then you can see that this will become, the characteristic equation will come out to be equal to 1 plus k divided by s into s plus 1. This equals to 0. This will be the characteristic equation. Okay. Now let us let me just solve this. This will become, the characteristic equation will ultimately come out to be equal to s square plus s plus k equal to 0. This we represent, if I represent it as qs, then the characteristic equation is s square plus s plus k equal to 0. Now the roots of this equation will be the poles of the system. The roots of this equation will be the poles of the system. So what are the roots of this equation? As you can see, you can just simply find out, this is a quadratic equation. So you can derive it using minus b plus minus b square minus 4ac by 2a. In that sense, this will come out to be equal to minus b. So coefficient is 1, minus b plus minus under root of b square, that is 1 square, minus 4 into a into c. So this coefficient is 1. Here the coefficient is k. So minus 4 into k into 1 divided by 2 into a. So the coefficient of s square is 1. This actually it's written as a square plus bs plus c. So from here only we derive the roots. So this will this is the if I say that S1 and S2, these are the two roots of the system, then the S1 and S2 will be minus 1 plus minus under root of 1 square minus 4k divided by 2. And I can also write this as minus 1 by 2 plus minus under root of, I am taking this 2 inside the root, so this will become 1 divided by 4 minus k. Okay, I hope this you will get it. It's simple maths that I've done. So these are the two poles of the system. But here you can see that we have got a variable. This variable is over here. This is k. So if I vary this value of k, the pole's location, there are two poles in the system. As I vary this value k, the two poles of the system, they are going to vary. Hence the position of the poles will vary, and we have to look into the position of the poles of the system. So just let us take how this position, these two poles will vary as we vary the value of k, and generally what we do, we vary the value of k from 0 to infinite. Okay, so first of all I'll just make a table over here. So I have got value of k and I need to find out the values of S1 and S2. First of all, I'll keep the value of k as equal to 0. What I'll keep this value of k as equal to 0, and hence here you know these are the roots. So if the value of k is equal to 0, the roots will be minus 1 by 2 plus minus under root of 1 by 4 minus 0. So this will become under root 1 by 4. That means this will become plus minus under root, sorry, not under root, plus minus 1 by 2. So one pole will lie at minus 1 by 2 plus 1 by 2. That means my S1 pole will lie at 0 only. And the second root will be minus 1 by 2 minus 1 by 2. So the second root will lie at minus 1. Okay. So if I want to plot this on the S plane, then you can see that when the value of k is equal to 0, when I am keeping the value of k equal to 0, then one of the pole it's lying at 0 and another pole it is lying at minus 1. Okay. Now let's increase the value of k. We have to vary it from 0 to infinite. So let me take some random value. I am taking the value of k as equal to 1. I am taking the value of k as equal to 1 by 10. Okay. So if I keep this as 1 by 10, this will become at k equal to 1 by 10, this will be minus 1 by 2 plus minus under root of 1 by 4 minus 1 by 10. So if you solve this, you will get one pole which will be lying at minus 0.112 and another pole it will be lying at minus 0.887. Okay. So the pole which is lying at minus 0.112 is this pole. Actually this S1 pole that we had taken, this shifts from here and it goes when we keep the value of k as 1 by 10. So this pole it shifts on the left hand side and the value over here it's 0.112. So the pole's location has shifted to this point minus 0.112. Similarly, this S2 pole that you had, this pole has shifted now from minus 1 to this point, that is 0.887. Okay. So this pole has shifted to the right, this pole has shifted to left. Now let's take another point, that is we will take the value of k as equal to 1 by 4. I am taking this intentionally, I am taking these values intentionally so that you get some insight about what is actually happening in the system. So now if I change the value of k, I increase it to 1 by 4, then you can see here in this expression, the value of k, if it becomes equal to 1 by 4, then this entire term, this will reduce to 0. So now both the poles will be lying at the position that is minus 1 by 2. This complete thing will reduce to 0. We have got two poles in the system. So these two poles will be lying at the same point. So that point will be minus 1 by 2 minus 1 by 2. Or I can say that now these poles have shifted. This pole has shifted more to the right. This pole has shifted more to the left. And both these poles are now at the same point. And that point is actually this point we are talking about. This is actually minus 0.5. So here the poles, these two poles have shifted. Next, if I again increase the value of k, now suppose I increase the value of k, increase it to 1 by 2, suppose. So what will happen? Now after you increase the value of k, increasing the value of k, making it greater than 1 by 4 will definitely make this term over here, this will become negative in nature. And this is root, so this term is actually become imaginary in nature. So if I increase the value of k, if I make it greater than 1 by 4, then what you can understand simple is that this term, second term, will become imaginary. And hence whatever values that you will be getting over here, that will be minus 1 by 2 will be the real part plus minus some imaginary part. And if you keep on increasing the value of k, then this imaginary part's magnitude will keep on increasing. The real part will remain same, however. Okay, so now if I increase, like suppose if I'm taking this value of k equal to 1 by 2, then uh, this will become minus 1 by 2 plus minus 1 by 4 minus 1 by 2. Okay, so our minus point, this will become point, this is 0.25 minus zero point 0.5. Okay, so here you will be getting minus, this will become minus zero point 0.5 plus minus under root of 0.25 minus zero point 0.5. So that is how you will be getting the values, or we can say the position of the poles or the location of poles will start increasing. Sorry. At this point if we are talking about, then the location of the poles will now move. They will be complex conjugate after the value of k increases from 1 by 4. So the complex conjugates will be in such a way that they will always be in pairs. Okay, so this is how your location of the poles they will look like. So actually what has happened is that if you see what happened is when the value of k was equal to 0, then there were two different poles. These were the two different poles. After a point, okay, these two poles they came and they collided. So two poles they came at the same point, and after a point, after this point has been achieved, one pole it went to positive infinity and another pole it went to negative infinity. And this we are deriving, just this is the numerical expression that is from where we are deriving this. This is how the location of the poles is being affected if we are varying the value of k. And had there been another system, then definitely according to the formula that the roots of that equation, we would have gotten another type of diagram over here. Okay, so now you see that this we have just done random mathematics that we have done, and we have found out the locus of the poles. Now we see that the system that we had taken, it was actually a second order system. Okay, this was a second order system. In second order system, we have learned that the system can be underdamped, it can be overdamped, it can be critically damped. So now if you are a control systems engineer and if you are given a requirement condition like the system, this should be the damping of the system and this should be the frequency of oscillation, then as an engineer what you can do, you will be able to keep, you will have to keep that value of k in the equation, or here the gain that you have. Okay, suppose it's given that the frequency of oscillation should be some random value. Suppose the frequency of oscillation should be equal to 1. Okay, so if the frequency of oscillation should be equal to 1, then you can see from here only, this is the characteristic equation. You can compare it with s square plus 2 zeta omega n s plus omega n square. So here actually the value of k is equal to omega n square. So if the value of omega n which should be equal to 1, then accordingly the value of k should be equal to 1. And you can see also over here that what is the value of k. If you already have the plot of the system, then you can easily make it, like if you want the value of omega n is equal to 1, then here you can just see if you have this root locus कि k की क्या value है इस point पे. Okay, so in that way you can easily find out that what should, according to the system's requirement, how will you be able to design the system, what value of k will be suited for a particular type of system. Suppose you want the system to be overdamped, suppose it's required that the system should be overdamped, then you can see that for the values of k between 0 and 1 by 4, फॉर दीज टू वैल्यू ओवर डैम सिस्टम की क्या कंडीशन होती है कि आपके जो पोल्स होते हैं सिस्टम के, दे आर नेगेटिव एंड दे आर अनइक्वल. ओके, डिफरेंट नेगेटिव पोल्स, तो वो केस में आपका सिस्टम जो होता है वो ओवर डैम्प्ड होता है. तो हियर यू कैन सी दैट व्हेन द वैल्यू ऑफ k इज लाइंग बिटवीन 0 and 1/4, only then you are getting over damped system, because in that case only you are getting two different unique poles. Suppose it's required that the system should be critically damped, then what should be the value of k? Then you should keep the value of k as equal to 1/4, because in that case only you are getting two equal poles. When poles are equal for second order system, then the system is critically damped. Then if you want under damped system, then definitely the value of k should be kept greater than 1/4. Okay, because there you can see that you are getting complex conjugates, and that's what you get when you have an underdamped system. If it's underdamped system, then what should be the damping, what should be the frequency of oscillations, that all you can determine. But for all that to happen, you should know that how the poles are moving as you're varying the value of k. Okay, so thus you can actually design a system by having the knowledge of location of pole. How is it going to travel its path as you vary the parameter? Okay, and now it's also not, it is not necessary that the parameter to be varied, like we are varying the parameter k. So the parameter to be varied is this open loop gain k only. This k is actually the open loop gain of the system. This is the open loop gain of the system. Okay. So it's not necessary that only this parameter should be varied in order to find the locus of the roots. You can vary other parameters also, but due to design considerations, this is the most handy parameter. This is what I perceive. So what we actually do is we vary this value of k, and accordingly we design the system. So in Crux, when we use the root locus technique, what we will be studying is that you vary the parameter, which is the open loop gain k, and you see how this affects the poles of the system. System can be as simple as that we had taken above, s k divided by s plus k. So the variation of k in that case we had seen, it was varying from 0 to minus infinity. The pole was varying from 0 to minus infinity. As the variation of k, it was done from 0 to infinity. Okay, and the farther a pole from the origin, like this is the origin. Okay, this is the origin. So the farther the pole is from the origin, jitna ye origin se dur jayega towards the left hand side or right hand side also, the higher will be the speed of the system. जितना दूर होता है, हमने देखा है नेचुरल रिस्पॉन्स उतनी ही जल्दी डीके करता है, तो सिस्टम की जो स्पीड होती है वो उतना ही फास्ट होती है. सो इफ़ यू वांट द सिस्टम टू रिएक्ट फास्ट faster, then you should make sure that the poles are lying, they are moving, they are much ahead of the origin. Okay, so farther is the pole from the origin, higher will be the speed, or you can also relate this with settling time. So as settling time is actually inversely proportional to the speed of the system, so lesser the settling time of the system, more is going to be the speed of the system. Okay, and lesser is the settling time, more will be the speed, and more will be the stability of the system. Okay, सेटलिंग टाइम को आप डिक्रीज करोगे, सिस्टम का स्पीड इंक्रीज होगा, स्टेबिलिटी आपकी इंक्रीज होगी. सो एक्चुअली इट शुड बी 1 by स्टेबिलिटी. मोर इज द स्पीड, मोर विल बी द स्टेबिलिटी. ओके, बिकॉज यू कैन सी ओवर हियर, लाइक इफ दिस इज द ओरिजिन. ओके, दिस इज एक्चुअली द डेंजर लाइन. ये आपका डेंजर जोन है. Poles को, for a system to be stable, the poles should lie on the left hand side of the S plane. So this is actually the safe zone. This is the danger line, and after that this is basically the dead zone. आपका system unstable हो जाता है. So if you want your poles to be farther from the imaginary, you will always want your poles to be farther from the imaginary axis for higher stability. Okay, so actually the knowledge of movement of poles can be really helpful to design any system. Okay, now if you are given, suppose such a if you are given any system, I'm taking another example where the characteristic equation it is given, suppose like s to the power 5 plus 4s to the power 4 plus 3s cube plus s square plus s plus k. Okay, this is suppose given the characteristic equation. So you can see the order of the system is 5. Hence, easily you can understand there are going to be 5 roots of the system. There are going to be 5 roots of the system. Now all you have to do is you have to find out all the 5 roots of the system, 5, 4, 3, 2, 1, whatever they are. You have to derive those poles of the system. Okay, and then they'll be in terms of k. So then you will have to find out, vary the value of k and determine that how the system's poles are varying. Okay, and then you can trace the path of the roots. Now, the obvious reaction of everyone will be, this is insane. It's not very easy. How can you find the 5 roots? Or even if the system becomes more complex, then you cannot simply find out all the roots of the system and then you vary the value of k, you take some random values and then you plot it. So that's not what actually root locus technique is all about. Root locus technique is not done actually in this manner. Aim will remain the same, that is, you have to trace the closed loop poles of the system as the value of k will vary, but not in the conventional way. So this was the introduction lecture where I wanted to emphasize what is the need of root locus. So what actually is done is that we have actually a set of rules. So you will be learning a set of rules for the root locus, and you follow those rules and then you make the plot. And the rules, these rules, they make the entire process very much easy, and then you can see the final results. Okay, also the variation of k, when we talk about the variation of k, it can be done like you can vary the value of k from 0 to infinite. When the value of k is varied from 0 to infinite, this is known as your root locus diagram. But you can also vary this value of k from 0 to minus infinite. Now if this is done, generally it's not mentioned in the books. In some of the books it's mentioned also. But when you vary the value of k from 0 to infinite, the rules will actually be modified to make the root locus. In that case, this is known as complementary. This is actually known as complementary root locus. Okay, and thus you can vary k from 0 to infinite, that will be root locus. 0 to minus infinite, it will be complementary locus. And if you vary the value of k from minus infinite to plus infinite, then this is known as complete root locus. This will be known as complete root locus diagram for any system. So in this lecture I'll wind it up over here. The rules we'll study in the next lecture. Thank you for listening.